Morning, everyone. Or should I say good morning 40% of the class, roughly speaking. I think I told you this would happen about the first week of class. People tend to realize that 8:30 is a bit early. All the stuff's available anyway, and that's fine. I trust that those of you who are still kicking around feel you get something out of being here in person, and I appreciate that. So far in the class, we've spent the first 10 lectures talking more or less about steel structures. We spent some time talking about the different kinds of shapes, properties of steel. We looked at the role of the gravity framing and the bracing and braced frames in steel structures. We calculated loads on buildings. So we looked at dead live snow as gravity loads, wind and earthquake as lateral loads. And we also considered the destabilizing effects of gravity loads on initially leaning structures through the application of notional lateral loads. We started to make the bridge between calculating the loads and doing the structural analysis to the member resistance stuff that we're going to be talking about for the rest of the course in lecture 10 on Wednesday when we started talking about limit states design. Basically, we already know that there's a probability that we're going to overestimate the member strength and potentially underestimate the loads that we calculated on our structures. And so what we're going to do is we're going to amplify the loads we calculate, and we're going to reduce the resistance that we calculate, and we're going to make sure that the reduced resistance is greater than the amplified loads, and that should help us provide an acceptably small probability that there's going to be any failure in the structure. So now we're moving on to the design of steel members in this course, and we're going to start today talking about tension members. Tension members, for the most part, tend to be the braces in your structure. You're going to be looking at tension-only bracing on assignment 2, not the design of the members, but on the calculation of the tension forces acting in those elements. We talked a little bit about what tension-only bracing was in lecture 4, but you could have tension compression bracing as well, so you might have to design braces for tension or compression. Members that are primarily tension members tend to be tension-only bracing in structures, and we'll see an example of what that looks like today. Basically, for the next, until lecture 21 or so, we're going to be talking about the primary modes of failure of tension members. We're going to look at both bolted members and welded members. It's common to bolt braces in the field, but we may also from time to time weld some things together. And we're going to look at the way that these connections can introduce different kinds of stress patterns in the members and account for those when we're trying to calculate the strength of those members against fracture. We're going to see this slide a lot for the next several weeks. Basically, we're going to be looking at how we're going to potentially rip these tension members apart. Ultimate limit states design, we want to prevent modes of failure that could result in collapse of the structure. We're going to want to prevent excessive yielding. We're going to want to prevent fracture at the connections. This one here we're going to introduce today. This is basically excessive yielding. We're going to look at this one for 2 or 3 lectures. This is going to be fracture at the connection. And then we're going to spend a lecture towards the end on this somewhat ugly expression. This is another way that connections can potentially fracture around the bolts, around the welds, and we'll unpack what each of these expressions means throughout the next few lectures. We're also going to look briefly at serviceability limit states. I introduced serviceability limit states in lecture 10. Sometimes we use load combinations. We're not actually going to use any load combinations to check this. This is just simply, is the brace going to be floppy? Technical term. Is it going to be easy enough to install? Is it going to rattle when the building vibrates in wind, for example? Those are the kinds of things that annoy people. And so we're going to impose this limit on the slenderness of the brace, basically the L divided by minimum radius of duration requirement, to make sure that we're not going to annoy people with floppy braces. Okay, so we're going to unpack these things over the next several lectures. And today is basically to serve to an introduction to some of these concepts when we're talking about tension members. You can get some more background if you're following the course textbook, if it was something that you decided was worth your while to purchase. Chapter 3 talks about tension members, and for the most part, I don't know what's in chapter 3. I haven't looked at it for a while, but we're more or less covering all the stuff that would be in there. I might go into more detail on some things than the textbook might go into, so if you're looking for some detail on stuff that I might not talk about, you should go take a look at some of those aspects in the textbook. So I showed you this picture the first day, And this was that school that was built recently on the north side. And I had given this as an example of a steel frame building that was relatively simple, but I also gave it as an example of a structure that would have something like tension-only bracing. We've got a brace here and a brace here, and if we've got loads acting in this direction, then we're going to have the brace that wants to push. It's not going to be able to push because it's flimsy. It has like a resistance of 2 or 3 kilonewtons. That's not going to help us much. So basically all that load's going to get transferred into the tension brace, and that's going to come through into the brace that's buried in the wall here. These braces are more or less going to just kind of give out of the way and buckle and not contribute significantly to the resistance of that building. And we're going to focus today and for a couple lectures on bracing that might look something like this. How these kinds of braces are connected. So this is the brace down here that's coming in. That's the brace. And it goes down, of course, all the way down here somewhere. And it gets connected into the beam and column interface through the gusset plate, right? This big plate here is the gusset plate. The gusset is connected to the column with a plate as well. The beam's connected to the column with a plate. When we're doing our structural analysis, we're basically, this is our joint, right? So that's our joint there. We can see that it's not really a an infinitely small joint. It's not a particle. It's a finite rigid body, but we're more or less going to assume that all the forces that come through these members pass through that single point. And so the tension in the brace is more or less going to work through that point. The potential for compression in the beam above is going to also work through that joint, and the potential for compression in this column is going to work through that joint. When we're arranging our bracing, we tend to want to make them what we call concentric. Concentric means that the loads in those braces all pass through more or less the same point so that we can apply our method of joints for our structural analysis, and then we expect those structures to behave the way that we think they will in the field. So this is an example of tension-only bracing. This is a flat bar, right? We talked about that in lecture 2. Flat bar is a common kind of structural steel member to use in a tension-only bracing situation because there's not much compressive resistance to a flat bar like this. From time to time, though, we might use WT sections. It's more common in industrial structures where we don't really care what they look like, and we don't really try to bury the braces necessarily within any kind of wall finishing. So if they're exposed in an industrial structure, we tend to use these WTs. They're often used as braces, and they're similar to flat bars because more or less the flange here of the WT is basically a flat bar. But then we've got the stem, or what's part of the web in the W section it's cut from, and that helps to provide some nominal buckling resistance. These are commonly used as tension compression braces in structures like this. For buildings with really, really heavy loads, we might even resort to using like a W section. Normally, W sections have significant areas. There's a lot of steel in these. You can fit a lot more steel into bigger W sections, and so the kinds of sections available on the market, pardon me, to use as braces or columns, we tend to have very heavy sections that we can roll using wide flange sections, and so this would be a very heavy brace that's expected to carry lots of load. And in this case, the flanges are connected to the gusset plate through a combination of the angles on either side that get bolted to the flange and to the gusset plate. In this case, we technically have two tension members. We have the W section, that's the brace, and we also have these angles, right? We've got angles that are basically forming that connection. And so the tension's coming from the W brace, it's going through shear in the bolts to develop tension in the angles, and then we basically have two tension members or two kinds of elements carrying tension in that kind of situation, and we'd have to look at the tensile resistance of both of those. Finally, it doesn't have to be a brace. It's not uncommon to have what's called a hanger. Often they're HSS sections because they kind of work nicely as hangers. Basically what a hanger is, it's an element that is suspended from, that's a beam up here, and then this element here is the hanger. And it's basically what you'd expect. It hangs the floor from this beam above so that all the load that comes in through the joist and girder elements that are framing into that develop tension in this hanger. And so that element's going to be carrying a tension force that comes from the gravity loads acting on that floor area to transfer that up to the beam to support the floor at that corner. Focusing on bracing though, just coming back to one of the things that we looked at in lecture 4, when we have bracing in structures, we communicate that on an elevation drawing or section drawing in 2 dimensions. And one of the things that's important is going to be that tension force or compression force that you are specifying on the drawings here. I'll remind everybody that this is the thing that tells the connection designer, who's ultimately responsible for designing that connection to be strong enough, what force you've designed that brace for. And so we don't actually tend to design the connections as the primary structural engineer on the project. We tend to size all the elements and then give the forces to the connection designers to make sure that they can design those connections. Okay, so this is an important piece of information, and so on assignment 2, I've asked you what kinds of information might be important to carry forward to your drawings. On assignment 2, you're calculating some tension forces. You're not going to start factoring them until later, but on assignment 3, you'll factor those up, and you'll basically have a factored force that you need to consider showing on your drawings. Okay, so basically after today, you should be able to identify a tension member in a steel building. I've gone through a couple of examples of where those might exist. Primarily, that comes from the structural analysis, and it should be pretty straightforward. But sometimes your tension members for certain loads might also act as compression members or flexural members in other situations. Whether or not something is a tension member or not just depends on the load case that you're considering. Then you should be able to calculate what we're going to be referring to as the gross section yield resistance of a tension member. That's the first equation that I showed you on this first slide of the course or of the lecture today. And you should also be able to calculate what's called the net section factor resistance of a simple member in tension with a simple bolt arrangement in it. Okay, so these are kind of the 3 things, all pretty simple today. I hope a little more relaxed than some of the previous lectures. Does anyone have any questions about these 3 things and why they might be important to us before we get into the material this morning? Okay, so maybe I'll just quickly put a poll everywhere question up here. It should be active, though I do have the thing up here so I can double check. What do you think we might be considering preventing in terms of failure of a tension member? Like, when would a tension member potentially result in collapse of a structure? Rely on some of the stuff you might have talked about in mechanics of materials or material science or whatever. What do you think would constitute failure of a tension member? There's some common themes here, I guess, so far. Fracture is an important one. I've mentioned that a couple times already this morning. Fracture is a brittle type of failure, and we want to make sure that we prevent that with a high level of certainty, right? Compared to something that might be a little bit more ductile. I don't see yielding here anywhere. We're going to see that yielding of our braces tends to be a ductile mechanism. It means we're going to see a lot of movement in our structure before we actually get collapse developing in the building, which can provide warning for people in the building to get out. And so we're not as worried. Well, of course, we're always worried about failure, but we're more worried about brittle failure. Stiffness is important, and we'll see that one of the primary drivers for why we're going to check the yielding of a brace is because once a brace starts to yield, it's no longer able to provide a stiff response that can prevent the building from tipping over sideways. And so once something starts to yield, the stiffness goes way down, and we start to get gravity loads more or less taking the structure down with it. And so that's an important thing. I do want to address buckling here. Buckling is something that happens when we have compression, right? We push on something, it compresses. That is not a tension member, that is a compression member. And so we will come back to buckling in lecture 22, I think, when we start talking about compression members. Buckling is not something we worry about for tension members because even if we have tension-only bracing, it takes some compression, it buckles. That doesn't necessarily constitute failure of the member. It's highly elastic, it happens at a very small load, and the tension brace opposite to the one that tries to go into compression takes up most of that force, okay? Brittle is important here. The connections, of course, important. Obviously, what we're trying to do is prevent overloading of these types of mechanisms or these types of members so that we have sufficient strength to prevent them from breaking or yielding excessively. So one of the simplest tension members that you've already seen before is a coupon, right? So in second year, I'm sure in second year, you load a coupon, you load it in the elastic range, you get a very stiff response. At a certain point, it starts to yield, and then it develops some strain hardening. ultimately gets up to this FU value that's referred to as the ultimate tensile strength. We have the yield strength. And so we have two stress values that we tend to work with. We have yield, which means that it's starting to no longer be linear. We stretch the brace significantly, and there can be a lot of movement. And what's very important here is we have a significant reduction in stiffness, right? E here is basically 0. There is no stiffness associated with that coupon when it's yielding. You're getting a significant amount of stretch for no additional load. Eventually it'll pick up again and we start to approach the ultimate strength. But once we reach the ultimate strength, that's basically it. If we have a load that's up here and the resistance wants to be down here, we're basically going to have a very quick mechanism of failure developing in that section. So what do we take away from this curve when we're trying to design tension members? Well, the first thing that's important is that the brace actually has to be stiff enough there to prevent the gravity loads from basically forcing it to fall over sideways. So let's say, for example, we've seen a structure that looks kind of like this before, but now instead of this delta just being an initial displacement, maybe we have a force that's from earthquake load or from wind load. Best to think about it in terms of wind load, so maybe this is something coming from wind, for example. And wind in that direction is going to put this little bar or rod or whatever into tension. And as long as the tension force is less than the yield force for the brace, it's going to be stiff. The stiffness is going to be EA over L. And so we can calculate the displacement, and there's enough stiffness in that brace to prevent this rod basically from swaying sideways. But once that brace gets to the yield load, that brace is going to stretch a whole bunch. We're not going to get any additional load from that stretch. And any additional load that we do start to get from strain hardening is going to be basically a moot point, because in addition to this lateral force we might have from wind, we also have a huge overturning effect now from this value P acting on these significantly enlarged lateral displacements. Okay, so basically the stiffness of the brace goes to 0 once it starts to yield. Because it's so long, we get a significant amount of stretch in it, and that's going to result in a lateral instability of the structures that we're trying to keep stable. Okay, so that means that this is something we're going to try to prevent with a reasonable amount of certainty, because yielding of this brace can lead to full or partial collapse of our structure. That's the first limit state we're going to talk about. The gross section yielding resistance. We want to prevent yielding of the cross section with a reasonable amount of certainty to keep the building stable. This expression and some of the stuff I'm going to talk about today are in the handbook around page 1-60. You have the second printing, the first printing, so it might be a couple pages off there, but it's around page 1-60 in the second printing. If you have the first printing, it should be on page 1-60. This is a pretty simple expression, and we've already seen most of the things in this before. In fact, in lecture 2, we estimated what we think the yield load of a pair of double angles with an area of 2,500 millimeters squared might be if the yield strength was 350 megapascals. And basically what we have now here is tacked on this resistance factor. And again, that's because we're trying to reduce the member resistance so that when the curves overlap, we're targeting a reliability index of about beta is equal to 3. It means it's a little bit more likely that you might have a tension brace in your building reaching its yield strength more often than you die by choking on your own food, as we talked about in lecture 10. The other things here, A I'd used before, is just the cross-sectional area. S16, the steel standard, uses subscript G, just to denote that that's the gross area, the full area. And the reason we have that is because we're going to be looking at other things like A subscript N, which means net area. Once we start poking bolt holes in, the area is going to change around our connections. And so AG is just A. For most of the sections in the handbook, it's just given to you in the tables. If you've got a plate, it's the width times the thickness of the plate. Of course, that's a rectangle. And FY is the specified minimum yield strength for whatever material you're working with here. Right? So basically this comes from the handbook, or gets calculated based on the dimensions of the cross-section you're working with. This is a standard value that comes from S16, and it's the targeted reliability index of 3. And this comes from the material grade. So for example, for 350W steel, which is most common, Fy is equal to 350 MPa. Okay, so if I tell you what the section is, you can look it up in the handbook, find A. 95% of the time we're using G40, 20, 21, 350W structural steel, so that tells you that Fy is 350, Phi is 0.9, simple calculation to do if you know what the cross section is. Right, so most commonly we're going to be working with 350W. One of the things to look out for if you're dealing with particularly thick steel, because really thick steel takes so long to cool, it ends up being a little bit softer, not quite as hard, and a little bit weaker than thinner structural steel. So if you're dealing with steel that's more than about 2.5 inches thicker, so you're going to reduce the yield strength to account for the fact that it cools a little bit differently, it doesn't quite get as strong. Does anyone have any questions about this expression, what it might imply for us, and why gross section yielding is an important limit state for us to prevent from occurring in a structure with a reasonable amount of certainty? Okay. So I had the opportunity when I was a teaching assistant for a course similar to this way back in the day, I think this was 2014 or something like that. And I had made a couple little test specimens, basically. So I've got a series of different kinds of bolting arrangements here. This is a thicker plate, right? So this is a thick plate. And then here I've got two back-to-back thinner plates. And they just have different bolting arrangements. I think the thinner plates are about 1/4 of an inch thick. I think the thick plate might be 5/8 of an inch thick, something like that. Drilled some holes in them, poked some bolts in them. And this white stuff that I've painted over is just basically a lime solution. And what happens is when you start to get yielding in this section, all that lime stuff starts to flake off. So it kind of gives you a visual representation of where the steel is starting to yield and stretch. And it tells us more or less how this thing is going to tend to want to fail. Okay, so this is a video that I hope plays. This is basically just a little sketch of what that specimen looks like, right? We've got the thick plate connected with bolts to thin plates. And it's in a machine that's pulling up on the thinner plates and down on the thick plates. And we're going to see more or less how this thing starts to get pulled apart. So basically, we've already seen it starting to stretch. There's a lot of flaking. We're probably yielding the thin plates. What you want to pay attention to is what's happening at this first line of bolts here. Right? A lot of flaking. It's yielding significantly. Lots of peeling of that whitewash, so there's a lot of yielding around the bolt holes. Of course, that's going to happen because there's less cross-sectional area there. And eventually, this thing's going to get pulled apart a little bit more. Up in the top is starting to yield. So we might have already reached the gross section yield, for example, of those thinner plates. The thick plate's not doing much. It's stronger. It's not going to yield. The thinner plates here are going to be the elements that end up yielding first. I don't know if I have sound on this or not, but I'll post the version with sound onto the course website anyway. We'll wait and we'll wait and we'll wait. You can actually start to see back here, the bolt holes are starting to elongate so much that you can actually see the hole right on the other side of the bolts. And so all of the stress is basically getting carried by the cross section immediately around that last line of bolts. We can also see at the back end some flaking around where the bolt is bearing perhaps on that back plate. We're going to look at that kind of failure mode in lecture 15 when we start talking about bolts. Eventually something's going to happen here. I'll let the tension build up. No pun intended. That cameraman sucks, doesn't he? I think what I'll do is I'll speed this up a little bit. Didn't even get much chance to see what happened there, did we? Right, so that was basically what happens when you get a significant amount of stress developing around the back side there. And maybe I'll just go back to that very quickly, see that again. It takes no time for us to kind of see this net section fracture type behavior from developing. Right, the bolt holes get really long. It's very quick, very sudden, significant release of the tension and elastic energy that's built up in that cross section. And basically what happens is where the area is reduced because we're poking bolt holes into this cross section to make sure that we can fit it together with bolts. Basically the thing's going to get pulled apart, and I don't know why it's showing you there again. Basically the part around the bolt holes gets separated across, and this is what's referred to as net section fracture. And we call it net section fracture because it's fracture, complete breaking, of the net section, where we've reduced the cross section to account for some bolt holes here. So basically we're developing more or less some stress on the net section, something like this. And that stress is concentrated over the net section where we've reduced it to accommodate the bolt holes. Even though it's yielding a lot, it doesn't move much, right? It's maybe yielding just over this little area here. It's not a significant amount of stretch. This yielding around the bolt holes is not going to result in instability of the structure because the yielding happens over a very short distance. It's not going to stretch by like 12 inches before it starts to fail. But what is going to stop the member from carrying any load and could potentially cause collapse is that fracture or breaking of the cross section. And it happens rather quickly when it starts to happen and in a rather brittle failure mode. Okay? So that basically brings us to net section fracture. We already know we have to prevent the brace from yielding so that it doesn't become unstable, but we allow yielding into the net section because it's short enough that it's not going to cause instability. But what could potentially happen after that area yields is it breaks at the ultimate strength at the net section. Basically what we have here is a smaller resistance factor, and we're targeting a reliability index of 4, and I've mentioned why that's important before. Why would we be targeting a higher reliability index for a failure mode like net section fracture? Why is that important? What does high reliability index mean? Lower probability of failure, right? It's a Z-score. The bigger Z is, the smaller the probability of failure is. And so we want brittle failure modes to have a lower probability of occurring. And so we're going to target a higher reliability index. That means we're going to reduce the resistance even more to provide that smaller probability. What we have here is ANE, which is called net effective area. And we're going to talk about what accounting for shear lag means in lecture 13. But for today, all we really need to know is that the net effective area for us for simple connections with well-spaced fasteners is just the net area. And so basically it's the gross area minus whatever cross-section we lose to accommodate the bolts. And then we've got the specified tensile strength, ultimate tensile strength of the structural steel. Okay, so very similar to gross section yield, except all the values are different, right? Different resistance factor, different area, different strength, but we're still trying to accomplish more or less the same thing. We've got a factor that's unitless times an area times a stress, which gives us a resistance in force. So what is gross area? It basically says gross area has to be calculated, and I don't know why it has to tell us this, but by summing the products of the thickness and the gross width of each element as measured normal to the axis of the member, right? I don't know why they have to tell grown adults how to calculate the cross-sectional area of something, but that's what they do. And our net area is determined by taking the critical net areas, which is going to be more important for welds later, of a segment along a potential path of minimum resistance. And basically, how we're going to think about it for flat bars is the net width. So we've got a width, maybe it's 150 millimeters, and we take 20 millimeters out here for a bolt and 20 millimeters out here for a bolt. That leaves us with 110. And that gets multiplied by the thickness for us to calculate the net area. Now, the allowance for bolt holes is interesting. We don't just say we've got a 20 millimeter bolt, and so the hole's 20 millimeters. Has anyone ever tried to put something together where the hole was exactly the same size as the bolt or whatever, like the peg you're trying to put through? Does it work? It doesn't work, especially when you have lots of different holes, because then the imperfections, like this hole is not quite aligned and this one's not quite aligned, you're never going to fit those bolts in. So what we do is we tend to allow, at least for a 2 millimeter larger hole than what's specified. Typically in industry, how it works is we've got imperial bolts, so we might have a 7/8 inch bolt, and they're going to drill the hole 1/16 of an inch bigger, so we've got a 15/16 inch hole. How we consider that in metric strength calculations is by making the bolt hole in our calculations 2 millimeters larger than the specified hole dimension. We also have a table in the handbook that tells us for different kinds of bolts which ones we should be using. And if we have holes that are drilled, that's nice. Then the specified, sorry. So the specified hole dimension here is to account for the fact that we need a larger hole than the bolt is. But we also have to add 2 millimeters if the holes aren't drilled. Does anyone know has anyone seen a hole made in a piece of steel before? It's kind of very specific. What do they do to make a hole in a piece of steel? Punch it, right? A lot of times it's just poof. When you punch a hole, you make the hole, of course, but all the material around that hole gets damaged too. It's a very quick, sudden movement. You start to move all the other material around. And so when you're punching holes through steel, the material around the hole is compromised a bit. So in addition to the hole that's going to be a bit bigger for the bolt, we're also going to add 2 millimeters for punched holes. But that can be waived if they're drilled because drilling doesn't result in the same kind of damage around the hole area. Okay, so if you're drilling the hole through the steel, you can waive that allowance. Basically, we need to make the hole a little bit bigger to accommodate the bolt. And if we punch them, we also take an additional 2 millimeters off the size of the hole, or add 2 millimeters onto the size of the hole when we're considering it in net section area calculations. So what does this mean for us? Well, for these simple kinds of flat bar braces, we've got the width of the plate, which is W. The net width is just going to be the width minus the number of bolt holes times the diameter of the bolt hole, right? So the width that we're calculating is this one across this area here. The bolt hole is going to be bigger than the diameter of the bolt, of course. So we're going to see some tables later that we can use to determine what the diameter should be that we're considering when we're doing this kind of calculation. Again, here, this is not hard math. This is grade, 4 or 5 math, right? We've got a line, we're taking 2 segments out of it. We've got a net width. It's how we're applying that math that might be a little bit more difficult in certain cases. This is the simplest case that we're going to come across when we're looking at these kinds of failures. So on the handbook on page 3-104, as I mentioned perhaps briefly before, the first chapter of the handbook is the steel standard. Everything else in the handbook is design tools or context for us to take the standard into consideration using. Basically, we're going to have primarily imperial size bolts. We'll talk about why that is later on, but for the most part, the bolts are going to be imperial. So the specified hole size is usually, right, like I said, about 1/8 of an inch bigger for most of the bolts. It's 1/8 of an inch bigger for other kinds of bolts, and so once you get an inch or bigger, you use an extra 1/8 of an inch to drill the hole. If you're using a 3/4 inch bolt or a 5/8 inch bolt, let's look at 5/8 inch. So if you have a 5/8 inch bolt, if you have drilled holes, you're going to take away 17 millimeters. If the holes are punched, you're going to take away 19 millimeters. Okay, so you can just use this table. Don't even have to calculate anything. They've made it as simple as they possibly could make it for us in doing these kinds of calculations. Okay, so I'd already mentioned before, but I just want to come back to this point and see if those of you who are paying attention can pick up the point that I've been putting down on the table. Basically, we don't want the brace to yield or the tension member to yield away from the connection. We don't want to stretch the brace significantly. So we say, well, we're not going to let the cross-section yield. But by definition, because we're using the fracture strength here, we are letting the steel around the connection yield before we develop the net section fracture. Why is it that we're permitting yielding at the connections when we're not permitting yielding at the gross section of the brace overall? Yielding always seems like something we don't want to have happen, right? Why are we permitting yielding in this case around the connections when we don't permit it in the brace itself? Yeah, it's very localized, right? You probably can't perceive between the left side and the right side, except the fact that the top head is a little bit positioned differently. But there's not a lot of brace deformation that occurs from that localized yielding. The pencil here might stretch maybe 1/8 of an inch due to that yielding occurring locally, whereas if I was to yield the pencil, it's going to stretch maybe 2 inches. In terms of lateral deformations and structures, this kind of localized yielding doesn't result in a significant amount of lateral deformation. We can still keep the structure stable. Once we lose complete load carrying capacity, however, of course, the structure can no longer be stable. And for yielding, we don't want it to happen along the full length of the brace because it's really long. A long brace can stretch several feet in the yield plateau, and that's going to result in instability of the structure when it's pushed laterally under wind load, for example. Okay, so we let localized yielding happen at the connection, but we prevent fracture with a reasonable amount of certainty. Whereas up here at the gross section, we do not want to have yielding developing at that section of the brace. Does anyone have any questions about what gross section yielding is, why it's bad, what net section fracture is, why it's bad, how we might apply those two expressions to calculate the resistance associated with either of those limit states? Okay, we're going to look at this example again. This is a close-up of that building that I showed you previously. This is just focusing on the top area. These are the upper braces here. So basically what we have is some tensionally flat bar bracing. They're connected to the gusset plates here with 8 5/8" bolts. And basically what we're going to do is we're going to look at what can happen at the brace and what can happen at the net section. We're going to focus on this brace here. And so the example is basically a 15 millimeter thick plate that's 150 millimeters wide. It's used as tensionally bracing in that two-story building that I showed you. The brace is connected to the gusset plate at each end using 5/8" bolts. We've got 8 of them. The spacing of the bolts looks something like this. So it was determined from the structural analysis that the factor tension force on the brace from wind and notional loads, for example, is going to be 580 kilonewtons. So this is actually the force that's specified on the drawing of this brace. I was able to actually see the drawings for this particular structure. And basically it said here, AF is 500 tension only, or sorry, 580 kilonewtons tension only. And so that's the actual force that this brace was designed for by the structural engineer. They picked a flat bar 15 by 150. The connection designer laid out the bolts and the gusset plate. What we're going to do here in the example, and actually what you're going to do, is you're going to determine whether the flat bar is strong enough to carry the factored tension force acting on the bar. Assume it's rolled with 350W steel. What I want to have happen here is this a little bit lopsided, perhaps, usually divided up by rooms, but for some reason this side of the room is more attractive than that side. So what I might say is this row, that row, and this row, and this row. All of y'all in the front corner, I want you to calculate the gross section yield resistance and see if you can get a value for that. Everybody else back here and to my right side of the room, try to calculate the net section fracture resistance based on the layout here. You can talk with your friends, you can try to calculate both if you're feeling a little bit bored, but basically I'm going to ask you to try it and report back, and then we'll go through the calculations together and see whether or not we can get on the same page for these types of calculations. I'll walk around for a bit, of course, so if you have questions, you don't have to just gnome at it and not ask questions. It's a good time to ask questions about something if you're not really sure how to start, what values to use. Just put your hand up and I'll come see you.
assume it's a punched hole.
You can assume whatever you think is reasonable to assume. Most people these days, especially for steel that thick, tend to drill. Yeah. Anyone have an answer for any of these things on either side? Maybe I'll ask you to put your hand up if you have an answer for gross section yield resistance. Does anyone have an answer for net section fracture resistance? I'll give you another minute or so to think about it. All right. What I usually interpret the discussion getting louder and louder as is either you're done or you're thinking about it and you're having enough time to think about it, but you're not quite gelling it enough that you need to chat about it. You might be asking, why do I get you to try these things first? I try to get you to try these things first because then you actually have to read the example and figure out exactly what it is you're trying to do. I can stand out here and tell you what we're trying to do and do it. It might not be necessarily clear. So if you actually have to try it, you have to understand what it is that we're trying to do here. And the other thing is, these are pretty simple expressions, but there's a lot of moving parts, especially the net section fracture. Okay, so it's good to see when you're trying it, like, oh, that looks easy, boom, 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 3 numbers multiplied together. But what should be a couple-minute problem can turn into a much longer problem, and then you start to realize, oh, I didn't really quite get that, or I didn't really quite get that. So when I go through the example, I can help you with those things, and it's more meaningful than me going through it. So the first thing we're trying to calculate here, or actually the first thing we're trying to do is recognize that there are 2 ways that this kind of brace will fail. The first way is that the brace could develop excessive yielding along the cross section and the gross section along the full length of the brace, or it's going to fracture across the line of bolts. And so we have to check gross section yielding, and we have to check net section fracture. Net section fracture is basically going to happen across a section that looks something like this, whereas gross section yielding is going to happen along the net or the full area without the bolt holes in it. So for gross section yielding, I'll just call it GSY. The tensile resistance is phi AG FY. Phi for gross section yielding is 0.9. AG, did anyone calculate a value of AG? Can anyone tell me how to calculate a value of AG for this? Yeah, the WT, width of the plate times thickness of the plate, right? The width of the plate is 150 millimeters. Thickness of the plate is 50 millimeters. That's WT, gross section area for this plate. And what should I take as FY? 350. It's 350 W steel. That means it's 350 MPa yield strength. And if I do that calculation, I get a value of about 709 kilonewtons. Again, this is going to give us something in newtons, right? 10 to the 3 kilonewtons. And so you're going to see me write millimeters, megapascals, and I'm not going to write the newtons. It's just going to be the kilonewtons. So I've got 709,000 newtons, or 709 kilonewtons. Okay, so that was the easier one. So y'all at this front corner had a bit more chance to maybe get an answer. Did anybody get an answer that was different than this, or does anybody have any questions or concerns about how we arrived at that answer for gross section yielding? Okay, next one is net section fracture. Okay, so that one is TR is phi U ultimate, ANE FU. The important thing here for us is that ANE is equal to the net area, and we'll talk about when that's not going to be the case in lecture, not to my next lecture, but the one after that. What's obvious here for us at least is that phi is 0.75, and that FU perhaps might be something else. How do we arrive at the ANE value for our net section here? Yeah. AN is ANE for us, so it's going to be WNT. WN is going to be the 150 millimeter width of the plate minus 2 bolt hole diameters. What should we use as a bolt hole diameter for the 5/8 inch bolts? Well, we can come to the table here. And one question was, do we assume drilled or not drilled? It's conservative to assume not drilled. At the same time, if you're the connection designer, you know what the people downstairs are doing. You're not going to be sitting in the office while you watch them build it and be like, are they drilling it or are they punching it? Like, you'll see them do it and you'll know what the people in your shop do. 9 times out of 10, they're going to be drilling those holes. Okay, so you don't have to err on the side of conservative. Most of the time, they're going to be drilling the holes, and you can take that value. So for us, we're at 5/8 of an inch, drill the holes. That tells us that for our net section fracture calculations, we're going to consider a hole diameter of 17 millimeters. Okay, that gives us something like, oh boy, my mental math skills. That's 34, so this should be 116 millimeters. That means ANE is 116 millimeters times 15 millimeters. I don't know if I calculated ANE or not. I get something like 1,740 millimeters squared. Okay, does anyone have any questions about that? What the values mean, or how we arrived at that answer for ANE? Okay, so ANE is 1740. We can plug that into the equation here. And of course, 350W steel, we're using 450 MPa ultimate strength. And we get a value of 587 kilonewtons for net section fracture resistance. Does anyone have any questions or concerns about these numbers, where they came from, or how we arrived at this answer? So those are a couple answers to questions that we're asking. The first question I'm going to ask is, which of these two things is the limiting strength for our brace? Net section fracture, right? We're expecting that if we overestimate, it's a very rarely weak brace. We're expecting to fracture at 587 kilonewtons versus yield at 709. So gross section yielding is not going to happen here. We expect the net section fracture to happen. Once it breaks apart, load carrying capacity is gone. We're not going to get any yielding in that brace. We're just going to fracture the connection. The next question is the brace acceptable? The strength of the brace is governed by net section fracture, 587 kilonewtons of strength. We've got a factored tension force of 580 kilonewtons. Are we good or are we not good? It's a real example of a real brace in a real building. We better be good, right? 580 is the force. Of course, we don't want to have less strength than what we need to carry. We have more strength, but it also tells us it's a reasonable design. There's not too much steel in there. It's threading the needle, so to speak. We have 587 kilonewtons of capacity versus the 580 that we need. Our TR is 587 kilonewtons, which is greater than TF, which is 580. So this is an acceptable design for this connection. Does anybody have any questions about this example? Any of the things that we went through? Why this is the governing limit state, 587 kilonewtons net section fracture, or why our brace is acceptable based on the resistances that we calculated? Okay, well, now you should be able to do these things, identify some tension members in steel buildings, calculate the gross section yield resistance of a tension member, and calculate the net section fracture resistance of a simple member with simple bolt arrangement. We'll talk about how things can be more complicated over the next couple of days. Does anyone have any questions about anything we've talked about today, or what these three things mean, or why these three things are going to be important to us moving forward in the course? Quiet crowd. We'll see everybody on Monday. Have a good weekend.